Welcome everyone. We're going to start our first topic for the year, and that's the scientific method. So when we're talking about science, it really is a process in which we're trying to answer these questions, but we're doing it in a way that is systematic, that is based on observations, and we're looking at this world around us and trying to understand how it works. So really, science starts as discovery. We're looking at all of these structures or processes or things that are happening in the world around us and sort of just gathering observations, gathering that data. Jane Goodall, if any of you guys know who she is, she's the one who worked with gorillas in Africa and really was just doing this discovery science. She's watching their behaviors and the stimuli and the interactions that are going on between the gorillas themselves, between the gorillas and their environment, and just trying to record all of that information before she really got into trying to interpret what those observations actually meant. So really, science initially is based on these observations. From there, we often end up making those inferences, which is really where she took all of this data that she was collecting, watching these gorillas, and started then inferring, well, all right, every time that this male gorilla came into the group, a certain behavior was elicited in others in the environment. That's an inference. So it's these quick logical conclusions that we make based on observations. And as she was watching these gorillas then interact with each other and making those inferences, she was starting to be able to refine all of this data that she was collecting, all these observations she was seeing, into really specific questions that she could then actually utilize the scientific method to start testing. And ultimately, all of this information that we gather can then be thrown in and compiled into potential generalizations. So we make these general conclusions based on all of these observations that we do. Now keep in mind with generalizations, however, we do this all the time. All right, this is sort of human nature to kind of observe, make these conclusions. If I see these similar actions happening around me over and over again and I come to the same conclusion, I tend to make these generalizations, right? So they describe patterns. But keep in mind whether we're talking just general everyday behavior versus science or both, there's always exceptions to those patterns, so be careful with that. But some generalizations we can talk about: generally, girls stop growing before boys, and for the most part that's true. Although if you think about it, I'm sure you've seen some boys who sort of hit their growth spurt really early, and girls who hit them later. Or it's always dark at midnight. Well, yeah, that could be true. But go to the North or South Pole and, well, maybe that's not, depending on what time of year you're there. So just be careful. We use these all the time and they're helpful. But remember that there are exceptions to those patterns, okay? So let's get into the scientific method itself. You've all seen this. This is stuff that you have probably been taught since elementary school, and realistically, you're doing the scientific method on a day-to-day basis. We talk about it as problem solving. You just don't necessarily think about it or think about every single step that we're going to discuss over the next couple of days. So, in general, if I were to define what the scientific method is, it's an organized way to solve a problem, and we do it through experimentation and observation, right? So it's problem solving, trial and error, using data that I collect through observation to ultimately get me some sort of answer to a question I had to begin with, right? So when we break down the scientific method, we often look at it in a series of steps, right? So every question is going to start with some observations. You're going to see something, you're going to see a process, you're going to see a structure and wonder maybe what it does. Well, there's your question. That question then We're going to talk about some intermediary steps, but ultimately that's going to get you to a hypothesis and a prediction that you can ultimately design an experiment around and actually test. And keep in mind that we teach you the scientific method in these steps, right? Kind of as a linear process, but realistically, science as a whole, doing good science, is a big cyclical process. So my test supports my hypothesis, great, and that probably is going to lead to some additional questions, in which case I'm going to end up looping back around and this process keeps happening. Or my test doesn't support my hypothesis, in which case I've got to go back, figure out, well, how do I adjust that hypothesis now given this new information that I've gotten from my experiments, and pose some new predictions, pose some new hypotheses, and adjust my experiment to now test those new hypotheses given the information that I had. So, although we're going to go through the scientific method as a bunch of steps, it's an easy, organized way to teach it and to learn it, but understand that real, true science, we are constantly looping back on other steps and working through this process as a whole. So let's start at the beginning if we were to work through this for a single problem. And the first thing I need to do is state what that problem is. What is my question? So I see some sort of event or reaction or structure, and I want to know what it is, how it works, why it works the way it does. What if I do this? Will that change the effect? Those sorts of things are what we're looking at this particular stage of the method. So let's take some really simplistic, elementary types of problems that you might have designed as an elementary student as a science fair project, right? So if I'm working through the scientific method and I'm looking at plants, maybe I notice that I've got this plant on my kitchen counter, it's really close to the sink, and so as a little elementary kid, I wonder why there are parts of the plant that keep dying, right? So I suggest, well, maybe based on the fact that it's really close to the sink and this is where we do the dishes, and hey, maybe I'm the kid who has to do the dishes in the house, that I tend to be a little sloppy, so maybe it's the soap that's killing the plants. So there's my initial question or my initial problem. Or let's take another scenario. So I go to the local carnival, I happen to win this goldfish in one of those carnival games, and I bring this goldfish home and I have no idea how to take care of it, but I know it needs to eat, so I wonder if there's a particular type of food that my goldfish might prefer. So they're really specific, simple questions, right? Now, if we're talking graduate level research, of course, these problems and these questions get more complicated, but for our purposes here, just to illustrate the point, let's stick to some simple problems like these. And we'll utilize these examples throughout our discussion about the scientific method. So, great, I've got these questions. Everybody from there immediately wants to jump into creating a hypothesis, doing an experiment, and forgets this really important step, and that's to go collect some actual information before I make a hypothesis. And I want to research my problem. And that research might come in the form of just going on the internet, seeing what kind of information is already out there. If we're talking our simplistic problems that we were just looking at, like the soap killing my plant, or what kind of goldfish food I should feed my new pet, the internet might be a really great place to go gather that sort of information. So you type those sorts of questions into Google and see what comes up, right? And think about even just everyday problem solving, right? I said scientific method really is about solving a problem. Well, most of you guys are high school students and either driving or going to be driving at some point. So let's use something that might happen to you at some point in the near future. You get in the car, and the car won't start. It sort of makes this grinding noise. you pop the hood, you start looking for things, right? YouTube. Right, how many of us have gone to YouTube to try and see if somebody else has had the same problem? Or how to fix it, right? So the internet's a great place to start. Now, if we're talking true scientific problems that you might do real research on, then we're probably going as actual everyday functional working scientists to scientific papers. And these papers really are, think about the lab reports you've written in the past. A scientific paper is truly a lab report that scientists publish to put out there as a way to tell other scientists, here's what my experiment was, here's what my results were, here were my conclusions, and they are great places to go as backup research for a true scientific experiment, which you may also come across on the internet, but most of the time you'll have to go either to a paid website or a actual physical journal is what we call them, scientific journals, and they're essentially like magazines full of scientific lab reports. Regardless, the point to this step is to give you some additional background. Has somebody already done your experiment and there's already an answer out there? In which case, maybe you want to do the experiment anyway as a way to just sort of back up and support that actual research, sort of confirm it for yourself. Or you take them at their word and not waste your time doing an experiment that already has been done and tested over and over and over again. Alright, so this is a really important step that a lot of people, a lot of kids forget, and yet it's incredibly important to make sure that we do. Now let's say that you go and you do some of that background research and you're still really not finding anything. You've kind of come up with this novel concept, which happens, especially in science. There are other ways to go and collect information at this step before you start jumping into building a hypothesis in an experiment. We can do just regular observations. More observations. So when we talk about an observation, we're talking about often using your five senses, right? Touch, taste, smell, sensing things. And sometimes those observations can be direct. You can actually see something. You can actually smell something. Other times it's indirect, in which case I may need to use some sort of technology, or I may need to sort of see its effects on something else because I can't directly observe the change. So indirect methods might be a way to go. Point is that these observations will often lead you to these quick logical conclusions, aka inferences. And they're going to be really important, especially if your initial question is really this big, broad topic that trying to design a controlled experiment around is going to be really difficult. And so having these extra observations, having these inferences helps you refine that general question into maybe a series of specific questions that you can ultimately design really good, thorough, controlled experiments to study. So what do we mean between observation and inference? Let me give you some examples. So you observe the doorbell ring, right? That is your observation. You're not making any conclusions about it. You're just stating what happened. The inference then is the logical conclusion that comes based on that observation. So if the doorbell rang, most of us, without even thinking about it, are going to quickly jump to, well, somebody must be at the door, so you're either going to go answer it or ignore it, depending on what your preference is. Alright, are you home alone, maybe? That kind of stuff. But the idea is that you're making this conclusion based on that observation. Here's another one. Mom saw you sneaking out. That's what happened. There's no conclusion, there's no effects being drawn from that. But, crap, Mom saw you sneaking out, right? So the logical conclusion is you're going to get grounded because you were probably not supposed to go out in the first place. So be really careful with these because a lot of students want to jump straight to the inference because it's just kind of where your brain goes. But if we're trying to specifically delineate the difference, an observation is simply stating what you see, what happened. The inference is the conclusion based on that. What's probably the next step? Or why do you think that observation occurred in the first place?